the project proposals, and they look appropriate. So I have looked at all four, and so the topic is appropriate. So there's a analysis of cascade prioritization techniques for web applications, and I looked at the references for all of them, and they seem to be appropriate. And so I'm going to look at them, and I guess I haven't looked at them, but if I will remember something that I have seen earlier that is related, I might just send you an email. I noticed that some of you have already used the two-column format that is needed for the final report. It is not required here, but it is required for the final report. Another is survey of techniques for fault-tolerant communication in embedded systems on chip. And, okay. Incorporation of test coverage in software reliability growth modeling. That's a good topic. That is something that we have worked on in the past. Cloud computing, quantifying reliability. This should be another good topic. And now I noticed that three of you have, as I had asked, included the main sources of information. That means 3 main conferences, 3 main journals, and 3 main research groups. So you should be, in research, you need to be familiar with where things are happening. So you should, if you haven't done it, I noticed that this, I don't see it in one of them. Then you should go ahead and do that. So I will, but you can start working so that the topics look appropriate. And we were looking at software reliability static factors. And so as I was saying, we will look at software reliability from 2 different, the 2 approaches are complementary. In fact, they have something in common. So one is the static approaches, and basically use of static metrics. Now some of you may have come across the term metric. So a metric is some kind of measurement. With software, they use a number of different metrics. For example, number of lines of code, that is a metric. And I was mentioning about a defect density model. So what are the factors that influence defect density? And I was mentioning phase is one thing that obviously impacts defect density, because as you keep doing more and more testing, the defect density would decline. Skill of the programming team. So if you have a highly skilled programming team, you will have lower number of defects. The maturity of the software process, and that makes quite a bit of a difference. There are the 5 SEI levels, and I have given you some numbers, which are basically kind of rounded version of numbers that I have seen in the literature. And I was mentioning about the structure factor. I was calling it FS. And one of the factors is use of assembly language. Complexity. And I was mentioning about the fact that there's a lot of disagreement. But consensus appears to be that In some cases, people have done some analysis about, they have tried to develop methods to find fault-prone modules. So if you have a project with a number of modules, they have attempted to identify fault-prone modules, and there apparently has been some success. So in that sense, you could say, but the decision is binary whenever they do that work. But I haven't seen any way of reliably connected complexity metric with defect density. So perhaps there is some dependence. In many cases, dependence has not been observed, that is statistically significant. And I was mentioning last time, possible reasons a dependence on other complexity metrics other than number of lines of code has not been observed. And module size is another one that we were talking about last time. And it is also somewhat controversial. I was mentioning about a study we did, and incidentally, I will be gone this coming Tuesday. So this time I will be gone to attend ISRI, so we are presenting some of our work there. And so I will not be here on Tuesday. So for Tuesday, we will do something different this Tuesday. So I will assign you some special reading. And also, we should have a test coming up sometime soon. So I think I should be assigning you some homework as well as maybe a quiz. So let me see what I can prepare perhaps today or tomorrow. So look for some homework sometime tomorrow, and look for a quiz. So possibly there would be a quiz, and also there would be a reading assignment. So instead of the class, you will read the paper. And I was thinking maybe I can have you read this paper, which is the module size versus defect density. And I will supply you the paper, basically what that we did, and see what you think about it. And there have been other studies, and I believe that other studies confirm our observations there. But see, search the literature and see what you find. See if you agree or disagree, and we will talk about it. So we will not have a formal class on Tuesday. Okay. Then I was mentioning about requirement volatility. So requirement volatility, that's a different topic altogether actually. So requirement volatility significantly impacts the defect density, and there have been some recent studies by people at Microsoft, and they mentioned that requirement volatility or code churn has a significant impact on defect density. Now, how do we use a defect density model? Now, you might recall that the model that we had proposed is this defect density equal to some constant and these factors. Notice that these factors are not necessarily linear expressions. So basically, each factor, so this is a function of phase, And for each of them, default value is 1. So idea is that you would compile your own submodel for a particular factor based on whatever is applicable to your process. Now I have given some tables which you could use as a guideline. In fact, you could use those tables to calculate numbers. But you process changes, so the applicable numbers will change. But let us assume that the numbers that I had given in the tables are the ones that are applicable. Now what about C? And notice that phase, I have assumed that the default, we are assuming that we are considering defect density at the beginning of the system testing phase, right? So assuming that we are talking about beginning of system testing phase, C could be in the range of between 12 to 16. Based on the data given by Musa. So based on the data that was collected by John Musa, basically from AT&T Bell Lab projects, and as well as other projects in other places, it seems to range between this, and assuming that D is measured in defects per 1,000 lines of code. Defects per 1,000 lines of non-commented source code lines. Now let us consider an example. Here's an example. Let us say there's some organization, and based on your past experience, you have found, one organization, and you have found that C is between 12 and 16, based on the past projects that your team has worked on. Okay, your team is average. Now nobody thinks that they are average, everyone thinks that they are above average, right? So, but let's assume that the team is average, nothing special about the team. So let's assume that the average team. Now even if it is by average, we actually mean, notice that you would have evaluated this value of C based on your own projects in the past. And in that case, you will have more accuracy. If you get the value of C from some other organization, your numbers may be slightly different. But if you have a number from your own organization, then if your team has not changed much, their capabilities, you could still call it an average team from your perspective. And let us say that SEI, maturity level, is 2. And 20% of the code in assembly. And other factors are same as for past projects. Same as for past projects. So you don't think that other factors have changed in any significant way from your past projects. Then you have to estimate the defect density. So D, here are the estimates. Let's make an upper estimate and a lower estimate. And for upper estimate, the C here could be as high as 16, multiplied by SEI maturity level is 2. So it's level 2. Okay, where's that table? SEI maturity level 2
default one.
Okay, so that's the default.